We'll click on it.
Got it. Yes.
कभी टर्न कर सकते हो कभी टर्न कर सकते हो बोर्ड ऑन करना बोर्ड पे भी शायद बोर्ड भी यूज करेंगे कभी टर्न कर सकते हो ना वो हाँ बस हाँ बट फिलहाल अभी के लिए शायद स्लाइड से दिखा दीजिए स्लाइड्स का शेयर हो रहा है ओह ओके ग्रेट थैंक यू
स्क्रीन शेयर है स्क्रीन पे जो भी है
Maybe 2 or 3 minutes more. We'll just wait for 2 or 3 minutes more. Or faculty wants to mention it. Yeah, 5 seconds. We'll start in about 15 minutes. So the faculty wants to know that's very interesting. So, good evening, all. So, this is our weekly seminar series where I'm happy to introduce our speaker for today, who's Dr. Mihir Bhattacharya, who is an assistant professor of economics at Ashoka University. He received his PhD in quantitative economics from the Economics and Planning Unit at his Institute Delhi, where he worked on problems in political economy and voting. He worked under the supervision of Professor Singh. Thereafter, he worked as a postdoctoral researcher at ex-Marseille School of Economics, where he worked on axiomatic social choice and political economy. And he worked with Professor Nicholas Gravel. And he's also been an associate member at the French Center for Social Sciences, CSH Delhi, since 2018. He has an excellent publication record and is published in top field journals like Social Theory, Social Welfare, Journal of Mathicon, and Journal of Theoretical Economics, to name a few. And he currently works, his current research interests are in the fields of social theory, decision theory, and political economy. So today he's going to present a political economy paper titled Electoral Competition with Single-plateaued Preferences. And as usual, so we have 45 minutes. Speaker will talk till 45 minutes, and then we'll have 25 minutes for Q&A. So thank you.
Thanks, Gopal, for the very nice introduction. And thanks for coming, because very close to New Year, so you're not expecting many attendees, but thanks to you. I think many of you have classes starting very soon, so you're here. Okay, so this is a standard paper in political economy, in theoretical political economy with single peak preferences. That is a standard model. And so what we are doing here is generalizing the single peak that was there in the model, modeling model, and making it a bit more general and allowing for plateaus at the peak, right? So instead of a best alternative, right, you'll have a plateau. So it means that the best alternative that you have is not a singleton, it's a plateau at the top, right? And then the standard single peak pattern will follow at the end, where preference dips as you move further away from that alternative. So there is nothing, the preference is not new. It exists in the literature, and I'll talk about that a little bit. But the modeling of an electoral competition on top of this type of preference, that is new. And so that's the main idea, and that's the outline of the talk. I'll start with introduction. The discrete model, I'll present the discrete model where you have a finite set of voters. So the policy space is still continuous, but the voters are finite. So it's actually finite model. And the continuum model where you have, in the beginning, I'll discuss the case where there are infinite voters, and voters are continuously distributed, right? So you have like a density function on that line. So everything is going to be on a line. As the standard down the model, if you're voting on that line. And then I'll talk about convergence. So what do we mean by convergence here? So it's this idea exists in some literature, but it's not very common in political economy, where we're asking the question that, you have infinite voters here and you have finite voters here, right? So can we define convergence in a sense that if the number of voters increases and n tends to infinity, where n is the number of voters, what you get as an equilibrium in the limit of the finite case, is it the same as the equilibrium in the continuum case for some conditions? Is it the same? Because it's a very common belief in many other theories in large elections and all, where you look at continuum of voters, we have infinite voters or sellers and buyers, where the question is often asked, what is the justification for continuous distribution? Because you don't have infinite players in any realistic situation, right? So what is the justification for that? Well, the justification here, that's what we're trying to get, is that the continuum model under some certain conditions can be seen as a convergence or a limit convergence to the limiting case of the discrete or the finite case, right? Where you have finite models. So that's the.
I think otherwise, always think of a single voter being insignificant, a group of voters being.
Yeah, that's an implication of the continuum model, is that the single voter is insignificant. But in reality, you may have a large set of voters, but we can argue that every voter is somehow significant in some cases, right? So there is still a possibility in the finite case for the voter to be significant or pivotal in some cases, but in the continuum that never happens. So realistically, it's difficult to argue why one should look at that, but we get that as a as a representation of the discrete case. I mean, of course, the math changes and they have nice properties there. So I'll go to the basic model. So again, I hope most of you know the basic single peak preference, right? That's the main result is that you have single peak preferences, right? So this is what single peak preferences look like. So if you have three voters, right? What is this dimension? I mean, it could be 0, 1, right? So the 0 to 1 dimension is basically a policy space, right? So suppose this is the percentage of government expenditure that you want to be done on public facilities or whatever. So or the tax rate that you're voting, right? So this could be any issue that you're voting on, which is linear, right? So you can always normalize it to 0, 1. And then it's why does single peak preference make sense? Well, if you prefer that 50% of the government expenditure should be spent on public things, public finance, public resources, then your preferences should, so that is your peak. That is the most preferred alternative is 50%, right? So if you decrease the preference, 49, 48, you're going away from your preference, so your preference decreases. So your from that policy decreases. The further you away you go from that. And similarly on the right hand side, you don't want more than 50%. So if the government is spending more on that, more on the policy, on that policy, then your preference again declines, right? So that is a standard assumption. And you can generalize it to many models which can be any policy which can be listed on an order from left to right. There are other models where you need not have a continuum, right? Like in this example, you can have discrete alternatives ordering them from left to right, and the preference can be single peak on that also. So here we would assume a continuum. So the policy space is a continuum. You can think of it as an interval. And so, given those preferences, the standard median mode theorem says that if there are two parties A and B, they must locate at the median, the ideal point of the median mode, right? So in equilibrium, both parties, what do parties want to do? They just want to maximize the vote that they will get, right? They have to locate here. Why? Because suppose one of them is here, but the other one is there, right? And it's very obvious that this person, this party who's there, will get the vote of this person because that's the peak. And that person prefers this policy to that policy. Anything further away is worse off, right? So he's getting a strict majority, right? And so the guy who is here could have actually chosen the same policy, and at least assumption is that then all the voters will randomize, right? Because the policy is same, so the voters are indifferent between both the policies, so they will randomize. So that is the standard argument that parties have no reason to deviate from the median. Because if you're both away from the median, then one of us can go to the median and get strictly more votes because of single peakedness. So you want to be close to the majority, as close to the majority as possible, and that's the only point, the unique point which is ensuring that. So that's the winning set. That's the Condorcet winning set, in other words, which means that if you choose that policy, it is going to defeat any other policy chosen by the other party in any pair-wise competition. It's a Condorcet winning set. It's a singleton set, right? And of course, if you have 4 voters, then the median set is an interval because you have the second and third voter being the median set, or you can define the median as the middle point. But again, the middle point will be the winning set here because you can locate in the middle. If you're not at the median, you can get more votes by locating in the middle. So similar results can be generalized in that case. So that's the standard median voter result with single peak preferences. So now we're saying that instead of peaks, if you have plateaus, right, what will be the result here? That's the question that we're asking here. So this is the literature that deals with this classic result, and we're generalizing on that. And so the assumption is that these parties are obviously motivated. They just want to win as many votes as possible. There are other models where this has been weakened or there are other motivations instead. For example, parties may have ideologies themselves, right? They have a preferred point, right? So if it's a very leftist party, it believes in some level of investment, government investment. So they have a preferred policy and they want to win the election, but they should understand that it should be close to that policy if they can. Obviously, in reality, we see that some parties don't even care about winning and they just care about ideologies. That's a very weakening of the rational assumption. But in this model, you see that we haven't buzzing that. So that is a refinement. We have done some extensions to those settings. But here, the only motivation is office motivation, which means that it's not to win as many votes, and so the median voters policy is very powerful, and there's a force attracting towards the median. So again, what is the justification or motivation behind single-plateaued preferences? Well, because you're not very extreme or rigid about your policies in general, right? I mean, you may have a preferred policy, like I said, 50%. If you want the government to spend exactly 50%, then generally you're not very rigid about that peak, right? I mean, you may be different over policies which are very close to it, right? So 49.5 up to 50.5. I mean, you may be indifferent in those policies. So it's only standard, or it's very natural to generalize that preference to this setting where you're indifferent over that, close to the peak that was there in the other model. Here, note that don't confuse it with the peak. There is no peak here. Everything is you're indifferent in the whole plateau. So I'll come to that diagram in a while. So that's the literature. The single plateau preference is not a new thing. It's been modeled in social choice and it's been characterized in an axiomatic setting with finite alternatives. And there is a very similar characterization of the Condorcet set that we also have, which we realized immediately after we had proved it. And so it's very similar to that. In fact, because it's a Condorcet set, his characterization of the set is the same as ours. It's just that we are motivating it through party competition, and he is just looking for the Condorcet set. And that's the starting point. So that is a common starting point, and then we're going to extend our results to the continuum and the convergence results. And again, so like I said, there's a social choice theory model here where he's looking at social choice functions over single plateau preferences, and he's imposed some axioms on that. And these are papers which are trying to characterize this kind of preference using some axioms for the individual choice model, right? So under what conditions this kind of preference makes sense axiomatically, that's the goal for those papers. Again, like I said, it's not a very common assumption in this political science and political economy model, even though single peak preference is very common. No one has generalized it to single plateau preference. So that's something that we are going to discuss, and surprisingly, yeah, the results are quite different from the median voter paper. So that's what I'll discuss here. And of course, we'll define what do we mean by convergence, and after we discuss the result for the infinite voters case, and we'll provide necessary and sufficient conditions. So the last theorem is still under construction somewhat. So we have some conjectures, but we are still working out the formal proof. So I have a sketch of that, and I'll try to present that. So anyway, comments are invited. Any suggestions, any comments, any clarification? If you have questions, please let me know, and I'll discuss that. So that's the standard model. There are finite. So in the finite model, finite set of voters, and we actually don't need to be odd. So that we can actually remove it, and I've known that for a while, but we're going to remove that. So it's not important, right? So in a standard downside model, you see that the median needs to be unique for a very nice result. Otherwise, we need to define a median as a midpoint or redefine it. Here, that problem is not there, and so we don't need n to be odd. And so there are two parties. So that's the policy space, just a interval in the real line, and there are two parties, A and B. They will announce platforms simultaneously, and after observing the platform, each voter decides on which party to vote for, and then the winner is chosen through majority rule and chaos and realized, right? So that's the game. But it's not a game where voters are doing anything strategically. So it's almost once the preferences are given, they vote for the closest policy. There's not much strategizing that they're going to do. They're going to just vote for the closest policy. So voters are almost silent players. Once the preferences are defined, we know what their strategy will be, and it's the parties which will decide where to locate. And again, we can starting that as taking that as a reference point, we can see whether they will locate somewhere in the median voters plateau or not. Right? That's so. This is the functional form. This xn minus xni is not. You can add a constant value here, and the whole preference will be the same. So if you add plus a here and here, it will be the same. So here it's defined in a particular way. So it's half the distance of the plateau, right? So this xni is defined as the half of the distance over the plateau. So in this diagram, you can see. So I'm assuming that this is the utility, right? So you can see that in the utility function. That's not important. We can add, we can scale it up and down. But here it seems like this epsilon I, why does it depend on the distance, the length of the plateau? It's not important. You can change that. So that's so for continuity, we need to ensure that the utility here is maximized, and as you go further away, it dips. So that's one way to write it. That's how we have written it, and you can scale it up and down. The exact utilities don't matter. It's just the characteristic of a single peak preference and the fact that the voters are indifferent at the top. That's the only thing that will matter for our results. And so we denote the plateau by this endpoints, lower bar xi and upper bar xi. That's the midpoint. That's not the peak, it's just the midpoint, right? So yeah, so given that parties want to maximize the vote share and voters have single plateau preferences, we can actually look at what their vote shares be by just looking at the endpoint. So that's how we have defined the vote share of the parties here. So just going back on that. Okay, so the vote share of party A, sorry, this should be VA. So that's the vote share of party A given their policies XA and XB is basically the number of voters. So the sum of these two types of voters. So these voters have the property that their midpoint of the plateau is to the left of XA and XB, the midpoint of XA and XB. So this is XAB. I'm calling the midpoint of XA and XB, right? Suppose XA is here and XB is here, right? So any voter whose midpoint is to the left of this midpoint, right? Midpoint of the plateau, this is X star I, right? So this is the midpoint of the plateau. We don't know what the plateau size, the length of the plateau will be. So suppose it is the right end point of that voter is to the left of XB, right? The right end point of that, the right end point of the plateau is to the left of XB, right? So if it is somewhere here, right, you can see that in this case, in this specific example, the plateau will be somewhere like this. This is the midpoint, right? It will be somewhere like this. Which means that the other party's position, XA, is on the plateau of that voter, right? Meaning that the voter is going to like that more than the other policy XB, which is outside the plateau, right? So anything outside the plateau is worse than anything inside the plateau. If both the policies are in the plateau, then the voter is indifferent. That's how the preference works, right? So using that property, we can write down the payoff, the votes that the parties will get. So these are the voters, these are the kind of voters that will surely vote for A. And then there are other kinds of voters, right? So what are the other kinds of voters? One voter is that whose plateau is across both the policies, right? Left hand point is here, right hand point is there. Obviously, he's indifferent between both, right? So you need to share the vote share. That's an assumption that they're just going to randomize or toss a coin and vote for one of you. So, or we can just assume that half, we win half votes. That's how we're defining it. And the other kind of voter that we're missing out here is that the voters whose midpoint is exactly at the midpoint of the party's positions, and the interval is within the two policies. So it's not across the two policies, but right in the middle. Again, they're indifferent because their endpoints are equidistant from either policy. Right? So that's again kind of voter who's going to be indifferent between the two parties. So that's the construction of the party vote share. Right. So in this setting, again, we need to define the Condorcet winning set, which is basically in the single case also you saw the any set is a Condorcet winning set if you as a party can choose any policy there and you are sure that you will win with at least half probability, right? So or you will win, either there will be tie or you will win with certainty. That's the definition of a Condorcet winning set here, and yeah, that's the definition of that set. Given that definition, we can characterize it as follows. So this is the winning set here. So note that in the single case with odd number of voters, it was just the median voters ideal point. Here it will be so what is X tilde? Well, you first rename all the endpoints. So when you have these plateaus, you have endpoints. Right, so you will just looking at endpoints. X1 lower bar, X1 upper bar, similarly X2 lower bar, and so on. So you just look at the endpoints, you just list them from left to right, and our claim is that similar to what Fishburne had found in 1973 is that with these party motivations, you will get the Condorcet set to be the set of points which are between the nth endpoint and the n plus 1th endpoint. So if there are n voters, you have two endpoints, right? Because each voter has two endpoints left and right. You just list them from left to right, ignoring whether so here there is no intersection, but I mean here there is no overlap of intervals. But it could be that x1 bar is here, but then immediately after that there's x2 lower bar, right? So we don't care about that. We just list all the endpoints as it is, left, right endpoint, or whatever. You don't worry about whether it's left endpoint or right endpoint. Just list all the endpoints from left to right, and then in that set of all endpoints, look at the nth and the n plus 1th endpoint. That will be the winning set, right? Note that it could be the case, depending on the distribution, that both these are left endpoints of some voter. Right? It doesn't necessarily mean that this will be an interval, this will be a plateau of any voter. It need not be the case. Here in this case, where there is no overlap, this is the Condorcet winning set because there is no overlap. But if there are overlaps in the plateaus, then it need not be the case that the winning set is a median voters full plateau. Right? And I'll show you an example of that. So given that is the winning set, of course, the equilibrium is that the parties will locate anywhere in that winning set and they will get exactly half of the vote share. And in some sense, you can say that they're both winning with equal probability, right? Or they're getting the exact same share. And then they can't do anything better than that, right? So again, just to compare it with the single pit case, because of the plateau, you get a interval, right? Of these n and n plus 1 endpoints, and parties can locate anywhere, and you're sure to win, or you're sure to get at least half of the votes, right? So the other party locates completely outside that set, then you get quickly more than half, right? But in equilibrium, that won't happen. In equilibrium, the other party could have moved inside the set and gained some votes. So that's so the proof of that. I want to skip the proof of that, but you can see through the diagram. Again, the proof of that is different from the Fishburne proof, because in the Fishburne model there was no party competition, but there was he has measured you studied the Condorcet winning set property, right? So using preferences, you can still locate the same set that we have found through party functions. So what is the winning set in this example? Well, you have 6 endpoints, right? You just look at 1, 2, 3, and that is the nth endpoint, right? So n is 3, and the n plus 1, right? So x1 upper bar and x3 lower bar. This is the winning set, right? And you can see that it's within the plateau of the median motor. The median motor in what sense? I mean, first of all, you have to think about what does median mean here, because there are no ideal points, right? So you can either define median by the midpoint. In that case, yes, this is not the winning set is not the full plateau of the median voters plateau. You can also define median according to the left endpoints. In that case, the left endpoint is this first left endpoint, is the second left endpoint, and this is the third left point. Again, this is the median. And similarly, so this guy is a median with respect to all. So here the structure is still you're getting very similar to the single peak case, because you'll get a median, you'll get a winning set which is intersecting somewhere in the median voters winning set in that in plateau in this case. But it need not be, and for that kind of example, you need at least 5 voters where the voter is not a median voter according to all these definitions, but there will be an intersection of the winning set with some median voters plateau, meaning the median according to either the left endpoint or the right endpoint, right? So there are 2 definitions of the median according to the left endpoint, and it could be a median according to the right endpoint also. So there will be some intersection according to either of those 2, but need not be both, right? Here, in both the directions, the median is the same. That's why you're seeing the intersection right in the middle of that, but it need not be the case. So that's the winning set. And so this is another example where the median can be defined according to left endpoint. So if you define it according to left endpoint, how many are there? 5. So the third one, 1, 2, 3, right? You can see that this is the median. If you just look at the median according to the left endpoint, this is the median voter, it's plateau. But you can see that the winning set is here. And how do you justify it? Well, it's the median according to the right endpoint. So the right endpoints, if you look at that, 1, 2, and 3, right? And you can see that this is the median voters plateau according to the right endpoint. And as you see here, it is somewhere in that. But that interval is so big here that, I mean, the result tells you exactly where it will be. It need not be the whole interval, or of course, in some cases, it can be a point also, right? The intersection of these endpoints is exactly at that same point. The nth and the n plus 1 endpoints are overlapping, right? In that case, the median, the Condorcet winning set is exactly a point. That can also happen. So these are some examples. Yeah.
Is this more like the intersection of the plateaus, getting the winning set is the intersection of all the plateaus? Will that be the case?
Yeah, there is some intersection. So in this case, for example, if there is no intersection, then it's the median voters. Right? There may be no intersection. In that case, or there may be intersections at the right of the distribution. So it's not sure that you're just maximizing the intersection. Here it is
Smallest plateau that is there in every, that's also not the case.
Yeah, not always, yeah. But like I said, this winning set will be in some median voters plateau. But the median, how do you define the median? It could be according to the left endpoint or the right endpoint. And it will be, yeah, given that it will be somewhere in the intersection where the intersection is maximum. And of course, the proof depends on showing that if you move out, you're going to lose more votes than you can gain. And that's the basic idea. It's a similar idea to single peak, but with the plateau. Any questions at this point? That's the basic result, and of course, so you can see that it doesn't distinguish between odd and even number of voters, right? So if you because you're looking at 2 n endpoints, so that's always going to be even, right? It means that you're always going to be picking an interval or a point depending on what the n and the n plus 1 endpoint is. But we don't care about the odd and even model, the number of voters. So that is not required. The odd assumption is not required. Now you can think about how the set will change if you add a voter, right? So if you add a voter to the completely to the left or completely to the right of that, then obviously the winning set will shift by one segment, right? Segment I'm defining as the set of endpoints where there are no other endpoints. So it will just shift one segment to the left if you add a voter there. It will shift to the right if you're adding a voter here. It will just shift one. It's similar to the median. You add a point there, the median will shift 1 point to the right. If you add a point here, the median will shift to the right. So those are the assumptions, those are the observations from this result. Yeah. Yeah, so that's what I said. So if you add a voter which is completely outside the winning set, on that side, it will shift there, unless there is an intersection, in which case, yes, it will shift to the lowest, it will shift to the closest voter. So this is the other example. Which one is that? Yeah, I think this is the one. So you're adding a voter J, whose lower endpoint is between the sorry, this should be n plus 1. Yeah, between the n plus 1. So if there is an intersection, right? Yeah, this. Right, so this was the nth and the nth endpoint. So obviously it depends where you add the voter, right? So if you're adding a voter like this, where the intersection has happened, right? So the nth one is shifting here, but the n plus 1 is will shift 1 here, right? 1 to the left. So this will be the new n and n plus 1 interval. Is that right? You're adding 1 here. Yeah, suppose there were 4 and now yeah, so it will shift to this one. Right? So earlier it was this one. And now the whole interval shift to this one. There may be some intersection depending on where you're adding it. If there is if you're adding a voter completely to the right, then it will just shift one segment from 3, 4 to 3, 4. That number 3, 4 will shift from here to there. And if you're adding a voter completely to the left, then the whole segment will shift 1 to the left. But if there's an intersection, then you'll have one interval, one endpoint shifting to the left and the other one remaining fixed, right? So here, this one remains fixed. But this endpoint doesn't change here. Only one moves in. Similarly, if you have an intersection there, then this one will move, but one of the other endpoints will remain fixed. So depending on where you, how the intersection is. If you're again adding an interval which is across the two, then again it remains same. Because you're adding 1 point there and here, so you're preserving the median property of that. So these are some assumptions. Why are these properties useful? Well, it is useful when you go from the n, when you're increasing n. If you increase the number of voters, these properties will be useful to determine how the winning set changes, right? So, like the example that you cited, if there are intersections, if I keep adding voters whose plateaus are intersecting, then this interval is going to shrink more and more, right? So intuitively, you can see that if I impose a restriction that now we can add voters, but there should be some intersection with the median voter, the earlier winning set, but not exactly the same winning set, right? So there's an intersection, but it's not nested inside or nesting the winning set. So there is some intersection with the complement and also the winning set. You can see that the winning set will collapse further and further, and as n tends to infinity, it will collapse to a point. That's the result. That one of the convergence results.
That's the intersection of the trigonometric add more voters.
Yeah, we're adding more voters and creating the intersection. The maximal intersection is going to converge to a point in that case, and that is where that we will discuss convergence. So that's the continuum model. In the continuum model again, yeah. No, you can have this. So
yeah, actually that's something that I was about to ask. Yeah, you could model it where players, voters are boundedly random. They can only see a part of the individual at any point. And I mean, especially with plateaus, I mean, the indifference thing, anything beyond what they can see, they are thinking of in terms of distances. So practical implication is this, it depends on which candidate comes to my door more and more. I mean, the visibility might not be there.
yeah,
So that's what you're asking.
Yeah, exactly. So there's complete information. Everyone knows everyone's status of facing the parties know. For the voters, it doesn't matter, right? Voter is just looking at her own ideal point and minimizing her own plateau, and then minimize the distance from the policy. Just going to vote for which policy is closest to the plateau, or if it's both in the plateau, then they're indifferent. But yeah, the parties know, so they can compute. Otherwise, there are other models where you don't know the median distribution, right? You don't know the median, but there's a probability distribution of where the median could be. Those models are also there. That means hard. There, you can have the assumption of privately informed candidates, where we have both different parties. You have a different prior over where the median could be. I have a different prior over where the median could be, and then you locate according to your point where it's maximum. The expectation is maximum of the median being there, and I have a different prior, so I locate somewhere else where I expect the median to be. And you see again divergence in that model because we have different information and prior about where the median can be. Those are other ideas that would extend this model. But this is a complete information. So everyone knows, the parties know the preferences of voters and plateaus and everything, and given that, so that's the starting point because we didn't know what happens in that setting. And so continuum model, again, the challenge we face here is how would you distribute so in a single peak case, you can just look at the ideal points and assume that there is a distribution of ideal points which is continuous. And again, given a continuous distribution of ideal points, you will have a single point is a median. Unless the distribution is not continuous, then you can have gaps and atoms. If there are atoms in the distribution, then you can have two medians or a range of medians. So suppose there are no medians in between, but the distribution is continuous piecewise, then you can have non-unique medians. But if everything is continuous, the distribution of ideal points is continuous. In that case, we get the continuous. You get one median unique point, right? So here we have assumed that the left end points are distributed continuously, and so are the right end points, right? So note that we haven't mentioned what happens to the intervals as such. How are they distributed? There are many examples that we are thinking of, and we will write that in the paper. But you can think of it as one example is that you take the full interval, that's one motor, keeping one endpoint fixed. Now you just vary the one endpoint continuously from left to right, right? So that in some sense is where one endpoint is continuously distributed across that, and I mean there is no distribution of right endpoints there, but the one endpoint is continuously distributed there. So that's the minimum case. Or you could also keeping that fixed, vary the right endpoint continuously, and so again you have continuous distribution of right endpoints in the interior. At the end it will jump because there can't be a right endpoint on both extremes, right? So it's going to be continuous only in the interior of that set. So again, those are examples. We just need some continuity in the middle. So basically, we need continuity of the total endpoints, right? Because if you remember, how do we find the winning set? It's by looking at all the endpoints, right? And how did we characterize the winning set? Well, it was the n and the n plus 1 endpoint, right? So the same idea here. Again, I'm not going to discuss this complicated looking integral. Is basically the same extension of the summation example that what are the voters, which voters vote for party A and which voters vote for party B. That's just adding the condition that you integrate over only those voters whose votes party A will get, right? So that's just, and then basically the voters who are indifferent, you're going to share those votes. That's you're integrating over those endpoints only, which are which satisfy those given properties. The same properties that we had in the finite case, right? So we are interested in the distribution of all endpoints, right? So again, if they are continuously distributed, both these distributions are continuous, both these functions are continuous on AB, then of course the additional function that we are adding to continuous function, they'll be continuous in that interval also. So that's the property that we need. Other than that, we don't really care about what happens with these functions. We just need the continuity in order to get a point. So again, the winning set can be characterized as, how did we do it in the finite voters case, n and n plus 1n, right? So what was it doing? That winning set is again dividing 2 and n points half, almost half, right? In the middle, the n and n plus 1 is dividing all n points in equal halves on the left and right of that. The same idea here. So if you have m as a mass of voters, right? So the winning set will be those set of points which divide this distribution, this mass of n points equally, right? So if mass of voters is m, the mass of n points will be 2n, right? Because they are twice the number. Here again, this is voters are half, but we're looking at the mass function, right? So again, given this property, it's easy to show that the winning set will be just a point, right? So in the finite case, we had an interval. Now with the continuity property and the continuous endpoints, it will have to be only a point. It can't be any interval. And why is that? That's just by the completeness property of the real line, right? Why? So suppose the winning set is not just a point, right? I'm not arguing for emptiness, because you can see that the set will not be empty, right? Everything is defined continuously, so there will be a point which is dividing the mass of n points on equal halves on either side, right? That will be well defined. It won't be empty. So given that it's non-empty, suppose for contradiction that there are 2 points x and y which are both in the winning set, right? But that will mean that there are no endpoints either left or right of it, right? Because you know that in the finite case also you can't have endpoints in the middle, because then it can't be the n and the n plus 1, right? The similar thing. You're saying that okay, this is the point where you integrate over the endpoints. Here it will be half, and there it will be half. But there's another point for which that property goes. So there must be a gap in between. But there can't be a gap in between. Why? Because the functions are continuous. So we said that the distribution of endpoints, left and right, or the total endpoints, the distribution of the total endpoints, that is continuous, which means that you can't have an interval. It has to be a point. So it's non-empty and it will be reduced to a point. So this is very similar to the continuous model in the single peak preference, right? So if you extend the single peak preference model to continuum model like that, you will also get a median, one unique median, and parties will locate there. So strangely, here you also get the same thing, because of course the plateaus, if they are continuously distributed, it means that every point is an endpoint, right? That's the assumption. It means that the plateaus also, either you can have very minuscule plateaus distributed throughout the interval, or like the one I said, where everything is distributed continuously, which means that there has to be a unique point which is dividing the endpoints equally. So the example that I gave, where you fix one interval and vary one endpoint from left to right, and then fix the other one and vary this one continuously, you can see that there has to be a unique point which is dividing the mass of n points equally. It has to be a unique point, right? So that's the assumption. So now, how much time do I have? It's done. 5 minutes. So I'll skip to this part and just get into convergence. So what do we mean by convergence? So like I said, if you have a distribution of n points given an n, right? Now you vary n, right? So suppose there was only one voter, there's a plateau, right? That's the winning set. Now you add another voter. What is the winning set? There's another winning set. Keep adding n keep adding more water and n changes from 1 to infinity, right? For each n, there is a winning set, right? You look at the winning set and the limit of that winning set, right? Is that limit of that winning set the same as the winning set of the limit of the distribution, right? So the distribution also, I mean, in many cases, the distribution may not exist. I'll give you an example, simple example of that. But if it exists, then then what is the limit of the winning set equal to the winning set in the continuum case, right? In that case, you can say that the continuum model is a limiting model of the finite case. That's what we are saying, right? That you can see that in many cases that may not be the case. Why? Because suppose you have these two motors here, right? And you have n by 2 minus 1, n by 2 minus 1 motors here, right? What does it say? Well, for n equal to 1, I think this is not well defined, but let's say 2 and above, you can define this property. So it's just saying that this is a distribution for every n greater than 2, for example, right? What is the winning set for each n greater than or equal to 2? Well, it is this set only, right? Because it's the only interval which divides the endpoints. This is the nth and the n plus 1th endpoint for any finite n, right? But this distribution is not well defined in the limit. Why? Because as n tends to infinity, this is infinity, right? And this is also infinity. So in that case, what we're doing is we're defining a mass function, which is basically looking at the limit of that divided by n, right? So when you take the limit of this as n tends to infinity, what do? Basically, divide the numerator and denominator by n, right? To get 1 by 2 minus 1 by n upon 1. As n tends to infinity, this is what? This is just half, right? So that is how we're defining the mass function. So using the mass function, what we are saying is that because in the limit, the distribution may not be well defined, so use the mass function to get the limiting distribution and then check whether the winning set in the finite case is it converging to the winning set of the continuum case, either when the functions are well defined and continuous, right? Or the functions are not well defined, but you have the mass function that it is converging to that, right? So in this case, what will happen? Well, if n tends to infinity and you're looking at the mass functions, what is it saying? It's saying that you're looking at the proportion, right? So it's half motors here, so half mass of motors, whatever, n, and half of the motors here, right? What will happen to this guy? The mass of this is 2 by n as n tends to infinity, so that is 0. So in the limit, that motor disappears, right? So what will happen? So why isn't convergence happening? Why? Because for every n, this is the winning set, right? So the limit of that winning set is also this set, but it is not equal to this set, which is the winning set in the continuum case or the limit case where we're looking at a mass function. Because when that motor drops out, that is not the winning set anymore. In the limit, this is the winning set. So again, what are those necessary and sufficient conditions for that? Well, that's what we have done. Just move to the last. So this is the definition of the mass function, and then some poetic justification here. Things fall apart. The center cannot hold. And our case is upon the hold. So it's just saying what is happening here. There is no mass in the center, right? So if the center cannot hold, then the resultant will also not hold. In the sense that convergence will fail if there is no mass at the center. So that we need. That is one condition. That's not only condition. There is some proportional conservation at the center. That also we need. Why is that? Well, that's the other case where you have n by 2 here, n by 2 here, and 2 motors here, right? So what is happening for every n greater than or equal to 2? I mean, this is the winning set, and in the limit, when you look at the mass functions, this motor drops out again because the proportion is 0 as n tends to infinity, and the sorry, so earlier it was here, and now when that motor drops out, it's this interval. The winning set shifts from this to this interval, right? So that is again not convergent. So you need that in the limit, the winning set. What that point is, it should have some proportionality on either side also. So even though there is positive mass in the center, that that convergence is not happening because the proportion drops, right? The proportion of endpoints or the mass of voters on the right for the finite case, this was the point that is maximizing the mass of voters, getting the winning set for any n. That was the winning set for any. So then the convergence are the same one. But in the limiting case, it just that voter drops out, and so the interval just shifts to the left. Right. So again, we're not getting convergence there. So these conditions, I mean, that's the rough proof that we have is that these two conditions are necessary and sufficient for convergence in the from the finite to the limit case. Of course, the first case is very trivial, right? For convergence, if the function is well defined, right? So if you take the uniform distribution of intervals, right? So every one nth partition of the interval is a voter's interval, right? That is well defined. And then to infinity, you're saying that every nth part interval or segment is basically a point in the limit. Is an interval of a voter. Their convergence is very natural, and there's nothing much to say here. It's just you just need continuity at the nth endpoint, and you get convergence of the two results. But if those functions are not well defined in the limit, then using the mass function also we can define convergence. But for that, you have those two conditions: positive mass at the center and the proportion conservation around those and the nth point as n tends to infinity. That proportionality should be conserved. Otherwise, these things will happen where the limit of the voter drops and the set moves to the left. So the winning set in the continuum case may not be equal to the limit of the winning set in the finite case where n tends to infinity. So those are not necessarily insufficient conditions for convergence in the limiting case. So I'll skip the proof, but that's the conclusion. So we considered a model of electoral computation with single-plateaued preferences, generalizing from the single-leaf case, and then showing the winning set, characterizing the winning set for the discrete case, which is also similar to Fishburne's. That's the disclaimer, and of course, then we're extending that to the continuum model where you can have infinite voters, but either they could be continuously distributed, or you could have them distributed in a way where they have a mass of voters here and here, and so it's not a continuous distribution, but it's a mass function. But you can still have some result. So we haven't added that result, but we can add another result for those mass functions also. And then given those two cases, we can define convergence. That's what we did. And convergence in the continuous case is very obvious. You just need in the limit, you want the function to be continuous at the endpoint, at the n and the nth endpoint, and obviously you get convergence of the two winning sets. But if you have mass functions, then you need those other properties where if they're not satisfied, you will not get convergence. So that's the main result. And of course, we're trying to refine that. So yeah, suggestions, and of course, we are thinking of other mixed motivation where we add where the parties themselves have policy preference. So they care about the policy. And given that I can win, if I can be closer to my policy, then I will move towards that policy so that I continue to win or continue to be tied the winning position. So the winning set is wide, and you are in some sense a leftist, then you will want to be close to the leftmost policy because you're still getting half the votes, right? So in that case, we look at the endpoints. And if you're someone who prefers the rightmost policy, then you will look at the right endpoint because there also you are still in the winning set. So you're both tying at the first place, you're both getting half votes, but instead of locating anywhere in the winning set, you will locate closest to your ideal point. Your ideal point would be on that side, on the extreme left or the extreme right. So again, you'll see divergence. So it's very natural to see parties don't always converge, right? They deviate and don't see centrist policies everywhere. That's the conclusion for that. So thank you for your patience and questions.
So do the results when the do you have the same problem that you have if you add more votes? Like if you have no candidates, like from 2 to 3.
Yeah, because in the three-party case, even with single-leaf preferences, you have the same issue. No, you don't have the equilibrium. Three parties. You don't have the equilibrium. So everything, falls apart. That's a separate literature in itself. You're adding multi-party equilibrium. You need to add more constraints or observations because note that for now, voters didn't need to be strategic. They just vote. There are just two policies. I'll vote for the closest one. But when there are three parties, then I may have an advantage voting for my second best because I know the first best may lose anyway. So their strategic voting comes into play. And but this continuum model helps because the individual voter doesn't matter, right? So if there are interesting things to be done there, we look at the aggregate strategy. So we have some voter type, and there is an aggregate strategy. If we deviate together, then that can be modeled where you get strategy tools for voting systems and electoral competition on top of that changing behavior. So that is a further extent. Thank you very much.
Any questions?
Happy New Year. Even if you say you're saying stepwise the party A. Well, if you know what the winning set is, it doesn't really matter. Right? So if you go first, you will look at the winning set only. The other party, even if it goes second, it will look at somewhere in the winning set, right? It can't do better than there's no, even that the winning set is well known, most of us, it doesn't matter. It depends whether you want the left side voters or the right side voters. That's only advantage. But in the end, if you're both locating in the winning set, you're going to get half only. That's the equilibrium. You can't do better than half if I am also located in the winning set. You can only at best half, you can get half the voter. Unless I don't know the winning set, and like the prior case where the priors are different, so you expect the median to be there, that's a different model. Yeah, no, so you think that you're adding another variable. So
Different instead of considering n different individuals, say n different socio-economic groups.
I think there is a similar model, Ray and Esteban, where they have measured polarization, and there they have characterized that voters form a group, and there's a group of voters there. So you can model it probably with mass functions where you have voters are all located at a point. They're voting as a group rather than individual. Right? Yeah, maybe there is something. Yeah, exactly. So there are results on multi-dimensional policy space also. Going back to plots, symmetry conditions. So you need ideal points need to be very symmetric around the given point. The conditions for existence of an equilibrium becomes very rare. I mean, the equilibrium becomes very rare in that case. So there have been advancements on that also, where you're looking at multi-dimensional space where ideal points are distributed across the space, and you have Euclidean preferences, right? So like a Bliss point type of preference. So that is your ideal point, and you have circular Euclidean preferences. As you move further away, the preferences decrease. There again, what people have done is they construct a line, they project the ideal positions to that line, and then they look at the median of that. There, what happens is you get more equilibrium. So that avoids the problem of having. You may get convergence on that line, but again, it depends on how you model it. So maybe we both have different lines that we're looking at. We don't know where the line is. That line is indicating how important an issue is, right? Suppose one dimension is more important than the other. So how the projections will look at will depend on what the slope of that line is. So the slope of the line is very steep, then you may get more distance on the line depending on the difference in one component. And if the slope is flat, the line is flat, then again we see the x component will become more important because the projections will be closer to the x value. So that depends. But you will still get equilibrium because when you reduce it to one dimension, you get a median somewhere, and you can again use what is that.
So if anyone is attending this online, if you have questions, course, let me bless it.
In the multi-dimensional case. Yeah, it depends. So in the traditional model where you need symmetry conditions, so whatever it's saying there's a point which divides the ideal points equally. So it's saying that the ideal points be distributed, so if you just take the extent plane, the ideal points be such that any line that we draw to that point, it divides the ideal points into two. So it means that you can have only ideal points divided as like the end of a square, right? That means that the center point of the square will have the property that any line that you draw along the center point has a property that is divided into the distribution into two equal halves. In that case, you have equal only at that point. Okay, so again, it's a very rigid result in the sense that you get convergence and the equilibrium at a point. But yeah, of course, if you're projecting it to a line, then again it depends on what that line is. Again, if it's a median, then it's again unique. So this unique equilibrium, especially for odd number of voters, and convergence to the median, obviously that is very persistent. Unless there is a cost of parties moving away from their policies point or there is policy motivation, only then you get. So in the mass function example where you have infinite voters, right, n by 2, and n by 3, for example, then you get the winning set to be an interval. There you have multiple equilibrium. Because you choose any policy, the other party can choose any other policy, basically you will get half of vote. But there's multiple equilibrium there. But the winning set is niche. That's the only winning set. You can locate anywhere there. I can locate on the same spot or to the right or less of that. As long as it's both in the winning set, we're able to get exactly half vote. Thanks. Have a good new year.
Thank you, everyone. And if you are interested in interacting with him, please be there in the canteen sometimes. Please want to join school. Tea and snacks are on the house.